Welcome to example number 9. We have a neutron that bombards a uranium nuclei forming barium, niobium, and 5 neutrons and 5 electrons. And they already give us all of these in atomic mass units. So these are all in U's here. So we're asked to figure out the amount of energy that is released if you have one atom of uranium and this neutron collides into it. Okay, so normally what I'll do first is I'll find the mass defect, which is the reactant mass minus the product mass. So you'll end up with basically, you should, if you're having energy being released, the final mass of the products should be less than what you started off with in terms of the reactants. All right, and this is called the mass defect. So the mass defect would be, well, we're going to take 1.0087 U's plus 235.0439 U's. So that's our reactant mass, and then subtract all of these. I've got the first two written, but these two where people typically make mistakes. You have to remember that your equations should be all balanced out. Sometimes you might need to figure out how many neutrons were released in here. But if you look at conservation of mass number, this is 236. That should be equal to 138 plus 93 plus 5. All right, so we have 5 times 1.0087 U's. Those are the neutrons. And then we have 5, and a lot of times we don't even neglect these because these are really small mass, but we're going to include it, 0.00055, and these are electrons. Electrons normally are not included because they have very small mass, but since it is being included, let's use it. And I get a mass defect of 0.19535 atomic mass units. Now, to find the energy, the easiest way, using Einstein's energy equivalence formula, is just to leave this in atomic mass units. So you would have 0.19535 U's, and then multiplied by, let's convert this to mega electron volts per c squared here. So we're going to multiply this by 931.49 mega electron volts per c squared for every atomic mass unit. So the U's cancel out, and we're going to get a units of mega electron volts per c squared. And then when we multiply by c squared, you'll see the c squares cancel out. So the energy is really this multiplied by this constant. This gives us an energy of 180, we'll just say 81.97 mega electron volts. Now you could convert the atomic mass units to kilograms and then convert that to joules. It's up to you. This is, by the way, the amount of energy per atom, or per reaction. Okay, now moving on to part B, we're asked to determine the amount of energy that would be produced if you were to have 1 kilogram of atoms. So first thing we need to do is find out, well, how many atoms are there if we have 1,000 grams of this stuff, right? 1,000 grams, or 1 kilogram, but we'll say 1,000 grams. And we're dealing with this nuclei, right? 1,000 of this fissile material, so uranium-235. So there are, if you think of atomic mass units, this is the amount of grams per mole that we have. So we have 1 mole all over 235.0439 grams. You can see the grams will cancel out, and now I have moles. And then what's the conversion between moles and number of atoms? Well, hopefully you remember from your chemistry that there are 6.022 times 10 to the power 23 stuff. Well, I guess we'll say the stuff is atoms per mole. So the moles cancel out. So our number of atoms is going to be 1,000 times Avogadro's number divided by the molar mass of, or the atomic molecular mass of this uranium. So that gets us 2.56 times 10 to the power 24 atoms. Now moving on to finding the total energy. Well, we know how much energy there is per atom, and we know how many atoms we have. So we just simply take that amount of energy, 181.97 mega electron volts for every atom, and we multiply by the number of atoms that we have in 1 kilogram of that uranium. So that's 2.56 times 10 to the power of 24 atoms. And the atoms cancel out. I end up with 4.66 times 10 to the power of 26 mega electron volts. But our answer listed down below, I believe, is in joules. Let's check that out. Let's convert the mega electron volts to electron volts. And in 1 mega electron volt, there is 10 to the power of 6 electron volts. So that's going to give us 4.66 times 10 to the power of 32 electron volts. And now let's convert to joules. We know that in 1 electron volt, there is 1.6 to the power of negative 19 joules for every electron volt. And that gets us an answer of 7.46 times 10 to the power of 13 joules. Now, you could have done this question a little bit differently in terms of you could have changed this atomic mass units to kilograms, all right, using the conversion at the beginning of the notes. And then multiply that in kilograms by the speed of light, which is 3 to the power 8, and square it, and then you'll get an energy that is in joules, and so you don't have to do the conversion stuff from mega electron volts to joules. It's really up to you. And that's it for this example.